I don't know where it. Can you put this? I don't know where it put. Okay. Good time.
We'll just wait for a few moments.
Okay. Full screen.
Okay, maybe we can get started.
Okay.
Welcome to today's string seminar, everyone. We're very happy to have Sreeman Reddy with us. He's going to tell us about quantum covariant bit threads. Sreeman, please.
Yeah. Okay. Okay. Hello, everyone. Thanks for giving me this opportunity. And yeah, like this is my project that I was doing in my master's a year ago with Matt Hedrick and Andrew Rolfe. And yeah, like two papers called Quantum Bit Threads 2 and Quantum Covariant Bit Threads 2. Sorry, Quantum Covariant Bit Threads. And yeah, I will review holographic entanglement entropy and then some older papers on bit threads and then like some new stuff like but if everyone knows the basics about like for example properties of quantum like RT formula and quantum external surface formula, maybe I can skip the first part, but like should I do the first part also, like the some review technical formula and the quantum external surface formula, those things? Yeah, maybe I will discuss that also, but I will try to fastly skip through it. Yeah, like the main result of black hole thermodynamics, if we recall QFT in curved spacetime, we have some formula S black hole is A/4, and in the classical case, it actually like the H bar goes to 0 and it diverges, but it's proportional to A, and this will always like increase. Like it is a thermodynamic quantity because it always like increases. Even in rare cases like Penrose process, the black hole energy decreases, the angular momentum decreases, but the area still increases. So it's Bekenstein interpreted this as some entropy, and we can also give this. It's not just for black hole event horizons, even for cosmological like killing horizons, any killing horizon, we can attribute entropy. That was the original Bekenstein, Hawking, and those people did the QFT in curved spacetime thing. But RT formula is a generalization of that. We need to first see that these are extremal surfaces. Like when we look at a black hole, like when we take some surface and keep the size decreasing, if we go inside the black hole, it's not in the same Cauchy slice. We are looking at a single Cauchy slice, T equal to constant in the square shell black hole. When we go inside the black hole, it's no longer like the R and T flip sign, and so like it's same thing happens in the cosmological case also. But in that case, we understand less well because like it has some weird properties. So and we don't have any Desitter CFT or something like that. But the killing horizons have entropy. Like that is one take home that QFT in curved space time gave that to us. And another thing is like next we will see that it is we can generalize it to arbitrary extremal surfaces instead of just killing horizons, which are just a small subset of extremal surfaces. Generalized entropy, like for black holes, A/4 is just order of H inverse approximation. If we want up to all orders, we need to add one more term S out. So it's just the entanglement entropy of the bulk matter fields outside the black hole. We are treating matter as quantum instead of classical, but the gravity is still classical. So it's semi-classical approximation. And this formula has a nice property that it's UV finite. When we put some epsilon cutoff on the QFT matter, then this A by 4 S out has some diverging quantity. It's A by epsilon square. A is here the boundary area of the outside. So it's outside the black hole. We have some the boundary is just the black hole event horizon. So it gets A by epsilon square, and here also epsilon goes to 0, and here also 1 by 4 G and G Newton minus 1 by epsilon square. And together this is more well defined. Each term alone is not well defined, but together they are better defined. Note that this UV finiteness is just for matter, not for the gravity. We are not doing quantum gravity. Then area will be an operator and geometry will be more complicated. I mean, we can do perturbative gravity, some small corrections to that, but this is still like geometry is classical. It's just
this cancellation can be shown by doing quantum field theory.
Yeah, in quantum field theory in Kurt's spacetime that can be shown. I think Susskind and Unglum or some they showed it in 1990s or something.
I don't think they showed it. I mean, I have a conclusion that this includes graviton fluctuation or not.
Yeah, I think the graviton thing, I'm also not completely sure. I think it's normal matter. They say it's matter, and the gravity generally, I think they did for up to one for QFT matter. I don't know if the gravity is included.
Yeah, because see, in n equal to 8 supergravity, this correction is at one loop, there is no correction, right? Because it's finite at one loop. So somehow that is confusing because the entanglement entropy always gets positive correction, right?
Yeah.
So how is the cancellation going to take place?
I'm also not completely sure about in quantum external surface formula, they just say that similar to this original formula, it's UV finite, but I think even this is already not completely shown.
Yeah, because there are examples where there is no correction to Newton's constant at one loop.
Okay.
Right, in extended supergravities. So it cannot be an entanglement entropy always gets positive correction, right? Whether it's bosons or fermions,
yeah,
they're entangled. So it doesn't seem that it's a general formula.
You are saying they don't cancel exactly like in the supergravity case?
No, in supergravity case, the Gn is not corrected.
Okay.
In extended supergravity,
Okay.
at least in n equal to 8
Correct.
supergravity, right? But there's a various finiteness analysis to very high loop order, right? So at least at one loop, there's no correction to Gn. Right? But the entanglement entropy, I would expect will get correction whether it's supergravity or not, because normally in supergravity, the Gn correction goes away because bosons and fermions contribute oppositely. Okay? But as far as the entanglement entropy is concerned, they contribute in the same way, right?
Okay. So they don't cancel out. This thing is not there, only this epsilon is there, okay?
Yeah, so I think that cancellation will not work in general.
I think these things they generally do in the classical limit of supergravity, like the higher corrections, like loop things, they maybe.
Ignore all higher corrections.
Okay.
But even n equal to 8 supergravity in 4 dimensions, people have checked up to some 4 loops.
Okay.
That is finite, right? So there's no correction to G Newton. So that means G Newton is not corrected. That's clear.
Is it a UV complete theory? Normally people say supergravity is not UV complete.
No, it's not UV complete, right? But this is also not, you're not talking about UV complete theory here, right? Because you're talking about corrections to G Newton without worrying about what completes it. In string theory also you can check. The G Newton has no correction, right? No, not even any finite correction. There, of course, there's no divergence, but there's no finite correction to G Newton when you include string loops.
So maybe the fact that this generalization is UV finite quantity is not a very general statement.
Yeah, it's not completely clear whether it's a general statement, right? At least if we define it this way, right? As renormalization of Newton's constant.
Yeah, like I think if we just fix gravity as classical, maybe then it is true. Like we don't.
No,
like,
gravity as classical means
clear.
everything will fluctuate, right? That says graviton fluctuation you have to include.
Yeah.
Right? Because they contribute to entanglement entropy also, right?
Yeah.
Graviton fluctuation.
But in a semi-classical approximation, we can take all fluctuations to be 0, right? Like we can take, so only T-level classical things are there.
But then what is this 1/4 Gn going to 1/4 Gn minus 1/? epsilon.
This
A
is
square.
like it's not a like the gravity is completely classical, but the back reaction of QFT matter that gives this thing.
Yeah, but that QFT matter should include graviton fluctuation, right? What is the difference between graviton and scalar field as far as small fluctuations are concerned?
But maybe in a semi-classical approximation, they don't contribute much. Like we are.
No, because a minimal coupling means that both gravity coupling to gravity and gravity coupling to scalar is controlled by G Newton, right?
Yeah. Okay.
So in no sense, the graviton fluctuation is suppressed compared to the scalar fluctuation, right? If you are just doing one loop correction to Newton's constant, right? So there's a parametric separation between gravity contribution and the scalar field contribution.
Okay. I'm not completely sure, but I think it's in many papers they say it by citing the Susskind and Bloom papers. So I don't know if it's done more properly in some latest papers or something.
I'm confused about one. I'm confused about the following. When you say S out, is that how is that defined? S out.
Outside event horizon of black hole, the entanglement between outside QFT and inside matter, like that is the like if we are just computing von Neumann entropy for.
So I take a surface which is outside the event horizon.
Yeah.
And then it doesn't matter how far outside the event horizon.
Yeah, it's entire space-time outside of the black hole.
From some surface up to infinity, right?
Yeah, up to infinity.
And that surface can be pushed back as close to the
It's the event horizon itself.
the horizon.
It's a fixed surface.
Except.
You understand the whole of outside.
So then, where is this divergence in S out coming from?
Entanglement entropies generally diverge. They have some boundary divergence, like so. The boundary of the outside is just event horizon. So a diverging factor will be always a by epsilon square, and then next term will be finite term. That is the more well-defined term. Okay, I will go
Computed semi-classically on the lattice.
Yeah. And this is like a drastic generalization of the original Bekenstein-Hawking formula. It's the same formula, but now instead of only for killing horizons, we are generalizing to arbitrary minimal surfaces. And in ADS-CFT, we give the interpretation of what is this entropy calculating. It's calculating the S of A of the boundary A. This is the boundary CFT, and A is the any arbitrary region in the CFT. And we are just looking at surfaces that are homologous. So they have the same boundary. That surface has the boundary same as A. And then we are minimizing over, like this is only, people often call it static case, but it's whenever there is time reflection symmetric case, then there is a privileged Cauchy slice. If it's static, like every Cauchy slice, it is same. But if there is a privileged Cauchy slice where there is symmetry t goes to minus t, then in that slice, we can look at minimal surfaces. This was the original Ryu-Takayanagi formula. And one main difference is the original Bekenstein-Hawking thing is a coarse-grained formula. This is a fine-grained, like for CFT, this S of A is a fine-grained, dependence on microstate.
I'm confused about your entropy S out.
This, okay.
So this includes gravity, right?
Like there is a classical gravity.
There's a classical gravity
and
component
yeah.
to it, and small fluctuations about the metric
Yeah, okay.
must be computed there as well. Okay, so then there must be a graviton in order to complete the calculation. You have to therefore calculate graviton contributions to
S out.
Yeah, S out as well as the first.
Yeah, it might also have entanglement entropy gravity, but I'm not completely sure if it's included. They generally say matter QFT. I don't know if it's gravity is included in that S out.
Yeah, but if you don't compute it, then the entropy counting is not complete.
Yeah, okay, yeah. Yeah, then H mu nu, the small perturbation is also included, yeah. Like in this case, RT formula generally says in the static case, if you know A, like on the boundary, you know everything on this region in the bulk. So similarly, if you know AB, then you know this entire thing. So if you want to know, for example, this middle thing, you need to either know AB or AC or BC. So it's like the information in the bulk is distributed outside, like in the, it's not locally there in the boundary, it's distributed. And some of the uses of the RT formula is that some proofs on the CFT side are much more complicated. The strong subjectivity is very complicated proof, but in this case, it's a single picture. It's just like this is the S of AB minimal surface, and this is S of BC, and then we can deform this surface, and this does not look like minimum, and the minimum will be that. So this is not, it is greater than the minimal surface. So similarly, we can I'm just showing some solutions where there are multiple external surfaces. In this case, for example, A admits two solutions in this case when there is a black hole. In that case, there is a phase transition, like when the length is actually like small, and if you change the length of A, like only for large A's, C becomes the correct thing. Normally, it's just this kind of surface that does not include the, like this thing also does not include the horizon, but it's including every blue thing outside the event horizon of the black hole. And another example, simple example is this, like when you have two systems, when they are close, the minimal surface is like this. A are CFT regions, and this has some mutual information, so they are sharing some information. But when they are far away, minimal surfaces are just, there is a phase transition and it becomes independent of each other. So they don't share any mutual information and it becomes zero, i.e. And the earlier formula was the static formula. Now the covariant thing is just extremize A by 4gn. So we just look at extremum and overall, not just on the single slice, but different slices. But this is not a very useful formula because like it is not telling whether it's minimization or maximization or anything else. Like, so there is a better thing called maximum formula by Wall. This thing was 2007 and this is like 2012. And this formula, you fix a single Cauchy slice, and on that single Cauchy slice, you minimize the surfaces, and then you also maximize all Cauchy slices. That is the case in the generic case where there is no static, like we don't have any time reflection symmetry, or it's not static, etc. And this is there, like this is more useful to prove strong subjectivity in the covariant case, etc. This formula is less useful for proofs. And there is another recent thing by Hedrick and Hobney called minimax prescription, and they introduced something called timesheets. And in the Cauchy slices, we need to only include slices that contain A. So in the boundary of the Cauchy slice, it should contain A. Here we include timesheets that touch the boundary of A. So this is the boundary of A and it is touching. And the timesheet, it does not necessarily have to touch like D of A. This is the one, the smallest thing where it touches D of A. Hedrick and Hubney, Veronica Hubney and Matt Hedrick. And they were doing bit threads in some paper, and in that they derived this formula. Like here we are fixing some timesheet. So this pink thing, we are fixing some thing, and then there are gamma surfaces on that. We minimize over, we maximize over all such gammas, supremum over all such, this is gamma. I wrote some typing mistake, I think. We maximize over all gammas on a single timesheet, and then we minimize over all timesheets, and we get the same formula.
Which one is the timesheet in the figure?
These pink color things are timesheet. Once you have a single timesheet, we maximize over this gamma. It's like different Cauchy slices. Gamma is some surface, any surface that has boundary of A. It's touching at the boundary. It's homologous to A. And then we are maximizing over all such gammas. And then we minimize over timesheets, different timesheets.
Instead of Cauchy surfaces and maximum formula, here I think timesheets.
Yeah, instead of Cauchy slices, we are using timesheets. Cauchy slices are some very old, from 1950 or something, it's there. But timesheets, no one defined for some reason, even though it's like very similar properties. And the causal structure, yeah, like the covariant thing has some causal structures. A domain, like the entropy of A is actually same as entropy of A prime. So entropy should be considered as the property of some domain of dependence. So in the boundary region, if there is some A, it's not a property of S of A, is actually more like a property of S of domain of dependence of A. Because there will be many surfaces that have same domain of dependence and all have same entropy. Like, and in the case of this, what is the dual for, we have this region D of A. What is the dual for this on the bulk? Originally people thought it's causal wedge, but it's not causal wedge, it's entanglement wedge. We just find the RT surface, and like we just find the domain of dependence of that surface. This blue thing is the RT surface corresponding to A. And domain of dependence on the CFT side is dual to this entanglement wedge. If we know everything on the D of A on the CFT, we can reconstruct everything in the entanglement wedge of the bulk. So there is a subregion duality, which is a generalization of the statement. If you know every operator on for every single operator of D of A, there is some mapping to operators on on this entanglement wedge. This is the subregion duality. This formula is only one such. We are this area of this surface is mapping to it is becoming equal to the S of D of A, and that is just one quantity mapping. But from ADS-CFT dictionary Z partition function of CFT equal to partition function of ADS, we can derive that all quantities can be there is a mapping for subregion to subregion. And quantum external surface is a generalization of the previous the covariant HRT formula. This is when we include matter quantum. It's called quantum surface, but it's not actual. The surface is just a classical geometry. It's quantum just because there is some S bulk term added here, and it's just the same surface here. But we are adding whenever we took this, we are taking domain of dependence of the this blue region and adding that S bulk also. S bulk of that R gamma. R gamma is just this region between gamma and A, and domain of dependence of that. Whether we write R gamma or D of R gamma here, it's the same. And yeah, this is a good formula. People say it's U finite and also IR finite. It's not IR finite, I think, but if we would take the mutual information, it's IR finite because the divergences in this, they will cancel out if we look at the earlier formula for this case, for example, it's these surfaces cancel out in the faraway region. So it's also an IR finite formula. And
as bulk in the previous slide, and does not involve graviton entanglement. It's only
generally people say just some scalar field or some some matter QFT. They don't consider gravitons. They generally just consider normal matter. And this formula is also not final. There are several generalizations beyond ADS. We don't have top-down string theory derivation for any de Sitter or flat space things. So these are more speculative. For this thing, there is a derivation from ADS-CFT from the partition function mapping in the dictionary. And here there are various generalizations in non-ADS. Some people define only for de Sitter. Some people define for arbitrary spacetimes, but they are more speculative. And also there is another generalization in ADS-CFT when we include gravity as perturbative corrections, and this is also they do some first order corrections in H cap, and already this is very complicated. I didn't read the thing fully, but they have area operator and some more complications. So and maybe this is also it's not non-perturbative gravity. They are just doing perturbative correction. So I think generally we are considering neglecting those graviton fluctuations. So that is again more complications, I think. But RT formula, whatever this quantum external surface, until this point, it's not speculative. Beyond generalizations are all speculative. And for this, there is a proof. This is RT formula of proof. And similarly, there are proofs for quantum external surface formula. And we just, for S of A, we just calculate we do the replica trick. We take this quantity, and if we take the limit n goes to 1, and that limit just gives the log of the normal entropy formula, rho log rho formula. And for this calculation, they do this replica trick. They find the partition function, take n copies of the CFT and glue it like that in the path integral. And in the case of so we need to glue n copies of ADS. And maybe I'll just skip that. I forgot some details. 1 second. Yeah, but in this case, it gives a tension. Normally when we consider point particles in general relativity or any theory, we do not consider the back reaction. These are test mass particles. But if you have a brane, it's not just the Namagoto action, because it might have some back reaction. Similarly, we need to consider some branes that give there is some conical defect. When you have n copies of ADS, we can replace that with a single copy of ADS. In that case, the contribution from the remaining n-1 copies, it becomes a conical defect in the ADS. To introduce that defect, we have to introduce some tension-full membrane. This is a proof by Shidong. It's a simpler version of what Levkovitz Madisana did. And this tension is n minus 1 by 4 times 4n in Planck units. And when we take n goes to 1, it becomes 0. So in that case, it becomes minimal surfaces. If we want to, instead of calculating entanglement entropy, if we want to calculate some nth range entropy, then we need to actually do some more complicated things because tension is non-zero. So it has some back reaction, but it's it's not a physical back reaction. It's an imaginary back reaction. We have some imaginary membrane. Only to calculate this, it has some back reaction. So the metric again changes, and then we calculate the surface again. But it is not a physical back reaction. It's not a real brane. It's just a trick. And now bit threads. So bit threads, like the basic idea is that we are considering all possible flows of through A and that have some norm bound here. So it's like divergence-less flows. So they look like this. The flows starting from A and ending on A complement. So each line is like one bit of entanglement entropy between A and A complement, and their divergence is 0. This is the classical static bit threads. So it's equal to the original RT formula, and it has some non-bound 1 by 4 in Planck units. Its modulus of V is. So then we have some simple tricks that we can do that, like the flux of V through A, it's always bounded by, the flux is same for any gamma surface. So it's less than any surface of, because divergence is 0, its flux through A is equal to flux through any random surface. So it's less than or equal to any random surface area because of the norm bound 1 by 4 GN. So we can, in the worst case, this happens, like we can maximize this side and minimize that side. So we get the minimal surface, and this this is less than or equal to, but we can actually show that it's actually always equal. Like whenever we maximize all possible flows, through this A, then this intuition is like if water is going through some pipe and it has some maximum velocity, so the worst case scenario will be the minimal surface that fixes the maximum flux of water, the amount of water that goes per second. So that will be the threshold bottleneck for the flow. So what are the optimal flows for this? They are highly non-unique, they are not unique. And the only thing we can say about the flux is that the norm mode is saturated on this gamma surface, the Ryu-Takaagi surface. And the remaining cases, the norm mode is not saturated. And in the remaining cases, there is a lot of freedom. In this case, the norm mode is saturated, and also the flux, it will be perpendicular to the gamma surfaces. The remaining places, except on gamma, we don't know the values for optimal solutions. In the static case by Andrew Rolfe, in 2021, some intuition is that each bit thread in this case is one bit thread is just one bit of entanglement between A and A complement. There is entanglement only in the boundary. In the bulk, we are neglecting entanglements. So, but now here we are switching on S bulk. So we need to allow for bit threads to start or end at the bulk. So we need to have some divergence non-zero terms. So the entanglement was only present in the boundary theory, but now it's also present in the bulk theory. And it's again the same max flux through A, but here we have some divergence constraint. This is number of negative charges in the region R gamma. R gamma is nothing but if this is A, R gamma is just this green line is the surface gamma. R gamma is just between A and gamma. So we are taking the S bulk of R gamma and then taking the divergence integrated over. So we are getting the number of negative charges should be bounded above by the S bulk. And this is true for all random surfaces. We take.
We need to reproduce the original entropy formula? Or?
Yeah, but there are also natural ways to derive from starting with that, and there are some very natural ways to get this.
When the original bit thread had no source or sink in the path, right?
Yeah, it's divergence 0.
Now we have to.
Yeah.
But what are the roots? What are the roots?
Roots means?
Where is the source? How much is the source? How much is the sink?
Yeah, like that is bounded, and we are maximizing flux. When we maximize, it becomes equal only for the RT surface, quantum external surface.
Maximizing what?
Like we are maximizing the flux. The program is S of A is equal to flux is maximized through A. So this is A. We are putting as many lines as possible from A. That is the number of flux. And like so, these two constraints are there, and accepting these two constraints, we want to maximize the flux, and that gives the quantum external surface formula.
But if you put lots of things, then you can put as much flux as you want, and it will just get sunk into the bulk, right?
But then it is violated, right? If we put too much negative charges, like the negative flux, then it is violated. We can put too much in the other direction. We can put too much in the positive charges.
I mean, to the A's bulk, there is something that you have to provide independent.
Yeah.
We are providing independent.
Yeah, we are providing, even in quantum external surface formula, if we want to minimize this A by 4 plus S bulk, we need to provide S bulk for all surfaces, all homologous surfaces to A.
Yeah.
Here also,
information you are not getting from.
Yeah, it's not, bitrate does not give you. CFT side, we know that, so we just, from the bulk QFT side, we know all the entanglement entropies, homologous to A, so all gammas, we assume that we know that. So, again, for optimal solutions, the norm on this surface will be saturated. So these flows, if we look at the norm, for the flow mod V at this point is always equal to 1 by 4 GN. And in the worst case, like it cannot go to the other side extreme case, because in that case it's like positive charges. So like they try to push the flux back, so it cannot maximize. It's not an optimal solution. If we do the maximization over flux, it always gives, this will be always saturated at one surface, and that is the quantum extremal surface. So these are like red threads which are having endpoints and they're jumping to the other side. Yeah, like most of these are normal classical threads, and these are some quantum corrections coming from S bulk. And by looking at the number of endpoints, we can say how much S bulk is there between A and A complement. And double holography interpretation, yeah, like in double holography, we have some bulk and CFT, and if we want to calculate S bulk in this thing, we are including quantum corrections in this bulk. To calculate S bulk in this, we take another higher dimensional bulk, and our entire area CFT is actually a boundary of this higher areas. But in that case, it's a classical bulk. There is no like we can interpret all the threads jumping as we can extrapolate this, and like the analog of A for the higher dimension is R of A. So this entire thing is just some region in the boundary of higher dimensional areas, and this is like that. So we can like this is just going like this and coming. So the number of red threads is the A by A4 of this surface, this RT surface in the higher dimension areas. If we calculate this higher dimension areas, it gives the number of red threads. So
the boundary, the higher dimensional radius is the lower dimensional radius.
Yeah, that is the.
So the radial direction of the higher dimensional one is vertical. The radial direction of the lower dimensional radius is horizontal.
Yeah, like the radial direction of this is the R equal to infinity of the. It's drawn in a weird way, but this is not the boundary of the higher dimension areas. Only the upper thing is the boundary of higher dimension areas.
And the red ones that were sunk in from the perspective of the lower dimensional areas, you interpret them as going through the bulk in the higher.
It is only giving S bulk. We have a CFT in some areas, but only for the calculating S bulk, we are using higher dimension areas. The gravity in the area CFT is not derived from the only the matter of this area CFT. We are only looking the matter, and that matter is imagined as the matter in these areas is imagined as a CFT of the boundary of the higher dimension areas. But in this bulk, apart from matter, there is also gravity. That gravity cannot be derived from the other higher dimension areas. So this area gives the S bulk term. This area gives the quantum external surface. Sorry, this area gives the normal A by 4, and this area gives the S bulk. If we add that, we get the quantum external surface. And so the generalization to the covariant case is we are relaxing the assumption of time reflection symmetry or static spacetime. So we are going to a covariant case, and in this case there are actually two different approaches, equivalent dual flows, U flows and V flows. and the V flows are these. Like we start with D of A, some domain of dependence, and we maximize the flux, and like I will show the formula. Yeah, like one good thing is like with area-based formulas, we don't know what is the dual to D of A. Like on the boundary CFT, we have D of A. What is the dual? Originally, people thought it was causal wedge. Then people found that it's entanglement wedge. So it's which is slightly bigger than causal wedge, is slightly smaller than entanglement wedge. In this case, it naturally finds the entanglement wedge, and yeah, I will show the definition. It's just flux, maximizing the flux. Some V is some one form, and D star V is 0. This is the divergence, like divergence is 0. And we can define the norm bound two different ways. I will just talk the first way. Like we can take an arbitrary time-like curve. So this is the V. We can take any arbitrary time-like curve. So when we take that and we integrate this V perpendicular thing on the time-like curve, it should be less than or equal to 1 by 4G. So like any arbitrary time-like curve, it should satisfy this. And for optimal solutions, what happens is just the norm mode is saturated only on the gamma HRT surface, the covariant surface, and whenever a bulk time-like curve touches this, it already saturates, so it cannot be non-zero up above that. So like above and below this I plus of gamma HRT and I minus of gamma HRT, it's completely empty. Only in the entanglement wedge of A and entanglement wedge of B, there is flows. So everything goes through this surface.
So how is V perpendicular defined?
It's just perpendicular to the bulk time-like curve. We take any random curve. So we take some random curve like this, and for that curve, there is some tangent, right? So we remove the tangential component from these flows.
And you integrate that?
With respect to T, like it's just some parameter on the curve. So we integrate over that thing.
Two regions now, A and B, D of A. Now you introduce D of B as well.
Like A complement is just B, like some places. So like this is the complementary entanglement wedge. And the other thing is U flow, instead of maximizing, it's a minimization thing. And I don't know if I wrote the formula here, but here also its divergence is 0. Like these are classical things. It's not quantum. It's classical covariant. And this is the same thing where they studied timesheets, same paper. And like here, everything goes to again gamma HRT. It's a minimization, and it will be greater than or equal to 1 by 4G in here. And like the norm bound is opposite. It's greater than or equal to 1 by 4GN, and we have a minimization problem. And it's again flux through this minus infinity I minus surface. That surface is the thing we are calculating. And like threads are just integrated flows. Until now, I called it threads, but it actually should be called flows. But if we integrate those flows, we get threads. And threads proofs are actually simpler in threads, even though like definitions are somewhat harder. Like to define them, we need to introduce measures and some little bit measure theory and things like that. But after we define them, like they're actually like easier to prove. This is the proof that U threads and V threads are dual to each other. And the proof is just like we have a program which is maximize mu, and mu is just a measure on these threads. So we have all possible threads, and we give measure such that like for example, in this case, the measure is 0 for all threads which are outside. So like this is the optimal measure that we get after optimizing mu. So we have some arbitrary measure. So we have random space like curves. Those things we are calling threads, and this is the program. It's measure mu is maximized like this. Capital P is the set of all possible threads, and we have a norm bound for every q belongs to time-like curves. This is the norm bound, which just says that for earlier what I said in the flows, that's when we integrate the flows, we get threads, and it's the same thing. But except in this case, I think 4GN is 1. Maybe I should have kept 4GN, but it's like 1 by 4GN in that side. And if for that thing we can write Lagrangian, it's just like Lagrange multiplier, but Lagrange multipliers we generally use for equalities. These are inequalities, so it's slightly different. Like this d nu should have some properties, and it has the properties like. And when we like this is similar to Lagrange multiplier. We introduce this and write like this, and then this integral d nu will come out as nu of q, and this we can write as integral over d mu, and like we can take this interchange the two measures on time-like curves, measures on space-like curves, and it becomes integral over d mu into 1 minus integral over, like this is some norm constraint, and then when we take the like this is some Lagrangian and this is like Lagrange multiplier, and corresponding to this multiplier we get this inequality, which is just the u threads. These are minimization program, and we are again, this is the flux of number of threads. It's just counting the number of threads, and for all space-like curves, here p was originally v threads. Now they became some random space-like curves. So here it's the measure is non-zero on only a few threads, but here we need to check for every space-like curve. Here also these are norm constraints. So for every time-like curve, we need to put that norm constraint and see like it should satisfy for every thing. But here the measure we are optimizing over, this thing is only non-zero on certain. It's only non-zero on certain number of, like in this case, only these threads are allowed. Other things it's not zero. Similarly, yeah, the quantum covariant case is just the mixing of these two, and we have some threads which jump, like v threads also get these dots and they jump over to the other side, and here also u threads also get some dot, like they have some endpoints and jump to the other side, and yeah, the divergence being zero, that we are replacing with this constraint. This is for the v case and this is for the u case, and it's just d of r gamma is we are taking some arbitrary surface, and d of r gamma is just domain of dependence of the interior region of the gamma. Like when we have some gamma, it has some r gamma between a and gamma is homologous to a, and like gamma is on this thing, and sorry, a is on the boundary and gamma is homologous to that. R gamma is the region between them, and d of r gamma is the domain of dependence. So for all such things, we integrate over, like in the optimal case, this is the thing, this region is the entanglement wedge. For non-optimal case, we are calling it as d of r gamma, and we are just integrating over the negative charges on that, and that should be less than or equal to S bulk of d of r gamma. So, and if we take the classical limit, we get the classical covariant case, because S bulk becomes zero in the classical limit, and these become divergenceless. Actually, there is like d star v equal to less than or equal to or greater than or equal to zero, but those things are in such a way that when we optimize over, it always prefers the if we take the classical limit, it becomes d star v greater than or equal to zero, but positive charges generally decrease the flux on d of a. So anyway, when we optimize, it essentially becomes d star v equal to zero. So they are the same programs when we take the classical limit. And the static limit, we are confining everything to a single Cauchy slice, and it just becomes the mod v less than or equal to 1/4 gen. The properties of optimal solution will be for quantum extremal surface gamma, like d star v. For all surfaces, the divergence inequality will be not saturated, but except quantum extremal surface, only for that it is saturated in the optimal case. Sorry. Yeah, like the divergence is saturated, and all the flux goes through single gamma, single surface, that is the quantum extremal surface. Again, this is the same, this norm bound is same as the classical. So this property is the same as the classical case. And bit threads cannot appear outside the two entanglement wedges due to the norm bound. When we maximize the flux, already the norm on the single surface is like it's already maximum allowed, so it cannot violate that. So whenever we take any time-like curve, it should have zero everywhere outside. So from that property, we can show that in the I plus of gamma HRT, like in the I plus of gamma quantum extremal surface, it's zero. Yeah, like in this case, like the threads in the quantum case, we have to introduce one more constraint, this constraint, and like if we start with this, like here what it is saying is like for all time sheets tau and for all like Cauchy slices sigma, we like this integral d mu is just some measure on like it's just some v thread measure. So for each thread we are giving some non-zero value or zero value, and we are averaging like, yeah, like this is just the divergence constraint. In the case of flows, we saw earlier, and it is same in the similar in the case of threads, and it's just less than or equal as bulk. And this is the norm bound in the case of threads. And like that, this is non-zero only when Q and P meet. Like Q is like for all random, this is like time-like curves. So V threads look like this, and the Q are some random time-like curves. And these Qs are continuous, but V threads have some endpoints, so they are not always continuous. So also like this thing looks slightly different from the like what we saw earlier, but like these two are same. Like if we convert this formula into the case of flow, it looks like this: D star V. It's the region between D of A and tau. Like the timesheet divides spacetime into two regions, one side and the other side. But it can be shown that this constraint is like enforcing on every timesheet, and in the limiting case, tau becomes the light-like time, like timesheet is piecewise like time-like, so it has some 1, D signature locally everywhere for timesheet. But in the limiting case, it becomes a light-like sheet, and that is when it becomes H gamma. Like, sorry, that is when it becomes like D of R gamma. Like,
What was H gamma? In the previous slide, I think.
Yeah, H gamma is just the boundary of D of R gamma. So like I will just show this. This is D of R gamma bulk region, and the boundary, this thing is the H gamma. Maybe in this, this is like 27. Once again. Yeah, like this thick blue line is the H gamma. So in this case, to prove again, the flows version is actually more complicated. The flows version is also I copied, but maybe I'll just skip the flow version. I will just do the like I will just show the proof for the threads case. Again, like earlier we saw threads. Like when we have this program, we have two constraints. So we need two measures to write a Lagrangian. One is a measure on all these Q are time-like curves, and this integral d nu is the measure on time-like curves. We introduce a measure, and into 1 minus, that is the norm constraint. And then the other thing, we have a condition on all timesheets and Cauchy slices. So we have a measure d rho and d kappa, and kappa is the measure on Cauchy slices, and rho is a measure on timesheets. And these are like averaging over, we are averaging over different timesheets and different Cauchy slices. So the integral should be always 1. Integral d kappa and integral d rho is always 1. But they have some averaged over distribution of Cauchy slices or timesheets. And then we do some simple rearrangement, and we get something called U prime threads. Like this just becomes like again, just like in the classical case, this same rearrangement gave from V threads to U threads. But here, instead of getting U threads, we get U prime threads. So we get this extra term. And this thing, yeah, that becomes when we convert it into a program that Lagrangian, like we are essentially optimizing over this this thing, and we get a constraint from that. This is true for all P, and P here is we started out with this V threads which have endpoints, but the norm threads like new, like these are time-like curves, they don't have endpoints. This new came here, so this new does not have endpoints, so it's like classical U threads, but this became the norm, this went into the norm constraint. So that thing has endpoints, whatever we started with the V threads. So here we get this constraint for every space-like curve. For every space-like curve, we have some norm constraint, but the norm constraint also has this divergence thing. It averages over all like all d rho and d kappa. So timesheets and Cauchy slices, and then we have like we need to minimize over number of U threads, and also minimize over this sigma is the Cauchy slices. We have to minimize over Cauchy slices and maximize over the timesheets. And yeah, like so like similarly we get V prime threads starting from U threads, and So it has some natural demarcation. There is an area term and there's S bulk. When we optimize, we get A by 4 here and S bulk there of the gamma extremal surface. But we can show this V thread to be same as, yeah, like if in the classical limit, this S bulk is 0 and V prime threads become V threads and U prime threads become U threads. Now, like by taking tangents, we can convert these U prime, V prime into flows. Flows are generally easier to look at. So I just converted it into flows. Here, infimum over U prime flow, and this is the flux on upper infinity like time. So it's like I plus is the infinite future. And we are minimizing over, it's like minimax, we are minimizing and maximizing our time sheets and cost slices. One of them should be minimized and other should be maximized. And we get this, and this thing, these U prime and V prime flows are like classical flows. They don't have any divergence. So this flux should be equal to any other flux, like just like in the classical case. So like the constraint interpretation, what is the interpretation of this constraint? We have a single constraint. These flows are like classical flows. They don't have divergence because these flows are coming from, when we do the dualization, they are coming from threads like we have V threads. From that we got these U prime flows, and V threads already had endpoints. There were some V threads which this V thread, when we dualize these things with endpoints, instead of being threads, they become non-constrained. And the time-like curves, which were earlier norm, in this case, they are norm constraints, they become the flows. So we get something which is like similar to classical U threads, but we have a S bulk extra term. And yeah, like the constraint interpretation is that if we take the full thread, like we can take any, like this is true for any space like curve with or without endpoints. So when we take without endpoints, they become a full curve. So this n is 0, like this n is measuring, like in this example, for example, this green, this is one space like curve that is going from here to here. But this thick green has endpoint. So that is a space like curve, but we can consider this other thick green which has no endpoints. So whenever we consider those kind of things, this n is 0, n is just the number of endpoints. So when n is 0, it's just the normal norm bound. It's just telling the flux should be integral of the space like curve. The norm on the space like curve is less than or equal to 1 by 4g. Sorry, it's u greater than or equal to 1 by 4gn. So in this case, like in the classical case, classical U flows, these thick green and the this light green, only the without endpoints are there. In that case, this thick green saturate the constraint because they are going through the norm bound here, and the light green does not saturate the norm bound. But here we also have some like instead of just full space like curves, we also have norm bound on curves with endpoints. So when we have endpoints, this n becomes 1. Like we're actually we need to average over many surfaces and many time sheets, and some of them can have n equal to 1 and some can have n equal to 0. But if we consider all the rho and kappa to be very closely, like the surface is almost the distribution is localized into some single surface, like then it's going to be like this thing has n equal to, like this already has n equal to 1, but it also has some non-zero this thing because it is touching these U flows. So this already it's like it's not saturating because just by being this, it already has 1, and like this is also not like the upper light green things are not saturating, but the thick green things are saturating the constraint. This thing, all the contribution comes from only on the norm thing, and that is already saturated and it's 1 by 4gn. And in the other case, this thing is just 1, and again it is saturating because this n becomes 1 and it's 1 minus 1 0, and this is 0. So it's again strictly 0 instead of some negative number. So for optimal solutions, what happens is for optimal solutions, it forces these like the relation, this constraint forces the U flows, this U prime flows to be in such a way that they go through either past or future of the surface, like this averaged surface. If we, in the optimal case, we anyway have single surface, we never have average over many surfaces. So when we localize that to a single surface, like for a single surface, this constraint forces all the V flow should be in that surface in the past or future, and so they have to be both the same surface. Whatever this is localizing, this should also go through the same surface. And then once we have the same surface, we can remove this optimization over U prime, and it's just minimax on our maximum formula. So this is they both belong to the same surface, and then we have to minimize together. This gives A/4, and this gives S bulk of that area, like of the same gamma, and then we have to extremize over that gamma. And that is one proof. Another proof is like using the flows, which is more complicated. I will just fastly skip through this. Like we start with here to average over, we use some functions phi and psi. These are they have some level sets.
What you just mentioned in the previous slide, should I basically understand that as your proof that?
Yeah, it can be done more clearly, but yeah, it's equal to quantum external surface. Like this proof going from U to V prime or V to U prime is very simple, and from there also it can be shown equal to like this is equal to quantum external surface, and it gives the this becomes A/4, and that becomes S bulk, and we have same minimax or maximum here over Cauchy slices and timesheets. So this just this constraint when we remove this mu or nu, it just forces this to be like A/4 plus S bulk, and then we average over timesheets and Cauchy slices. And anyway, when we optimize, the average is gone. It's just if we do, these are called relaxed quantum external surface formulas, and they are like we are minimizing over average surfaces. Like we are here also, this is another type of relaxed quantum external surface formula. But when we optimize this also, it gives the same thing. Here, phi and psi, they are some functions, and we have some level sets. Level sets, whenever we fix phi, some phi is either t somewhere between -half to half. When we fix that, we get some timesheet, and like this sigma t and tau s. Tau s is the timesheet corresponding to psi, and similarly sigma t, like those two we get. And like here, I will just skip through this and.
You can take up to like half an hour more.
Yeah, okay. But yeah, like here we have we introduce the Lagrange multiplier, and it's to enforce some constraint, and that Lagrange multiplier becomes the V flow. Even in the quantum covariant case, it becomes like that. This is just brute forcing the whatever proof that worked for the classical covariant case and adding S bulk terms, and it mostly works, but it's more complicated than the threads case. And finally, we get this kind of thing where we have to remove this maximization, and like this inside we have this thing, and this constraint, like d of a, like from this we can get a constraint that timesheet on the side of d of a, that we get that kind of constraint, but we can take like that constraint is actually the same as just taking d of r gamma, because in the limiting case, like the worst case scenario will be when timesheets become light-like and it becomes like d of r gamma. So once we remove that, this maximization becomes useless because this phi is no longer in this, and in that case there was phi in this, like this integral over dt and ds, those are they have phi and psi. But anyway, I'm just skipping the proof, and here also some details about proof. And yeah, like this is another entanglement distribution functions, and we can define some new quantity on the any QFT. This is called entanglement distribution function, and it was useful in our case. Normally, entanglement entropy is not a local quantity. We cannot say some function f of x at each point in spacetime. It's a local measure of entanglement entropy. It's not possible. But we can say that for every region, for every d of a, we have some integral, and it's always less than or equal to s of a. For every possible a, it's always true in the boundary CFT. We can find some functions like that. They only saturate for few surfaces or one surface. And when we have that function, and when we map, when we can map that function to the flux v dot n. So like there is a mapping from these boundary entanglement distribution functions and bulk flows. And when we optimize, it saturates, this saturates, it becomes equal to S of A only for the surface A where we are optimizing. In the case of finite degrees of freedom, this integral is just some, for example, if we have finite degree of freedom, like some multipartite entanglement entropy, where A1, A2, etc., and so on is the some ABCD, some 4 systems, and they have entanglement entropy, like we have S of AB, S of AC, etc. Similarly, like in the case of finite degrees of freedom, we just sum over these things. Like if you consider AB as the system, it's just sum over like A and B, individual entanglement entropies locally. Like if this A is, for example, some equal to A1 union, A1 and A2, then we sum over the discrete degrees of freedom. And in that case, we can consider a vector f of A1, comma f of A2, and so on. So it's like measuring this local function at each point. This is a discrete system, so the degrees of freedom is just a many-body system. And that vector, if we draw for different like states, it encodes all the entanglement substructure, and it's called entropohedron, and we like can find the like shapes for different states, and it encodes all the like not only S of A for all subsystems. In the continuous case, the shapes will be more complicated, but this is for bipartite and this is for the tripartite system. There are 3 degrees of freedom. Locally, it's just ABC in this case, and f of 1, f of 2, f of 3 are the entanglement entropies of S of A, S of B, and S of C.
You define this entropy distribution function as just any function where when you integrate
Yeah.
determinants of A, it must be less than S of
Yeah.
And how do you calculate this F1, F2?
This D of A is just in space-time, there are infinite points. At each point we have some value, right? This is on the CFT side. Or any QFT, even if there is no holography. In the case of holography, we have some interpretation that it's V dot N. Yeah. Yeah. In this case, it's a discrete system. So instead of f of x at each point, we have some many-body physics. So we have particle 1, particle 2, and things like that. So at each point, instead of each point, we have like entropy of particle 1, entropy of particle 2, etc., and entropy of AN. And this F is measuring their entropy. This F is less than their entropy, but not necessarily equal to their entropy. We calculate all such F and draw them in some like n-dimensional, like if we have n degrees of freedom, it's like n-dimensional space, and it like if we calculate them, it gives some information about the state, all the entanglement substructure of the state. If we, for example, take it's just sum over, this integral becomes sum. So if the region like you are considering is like AB, then we just sum over f of 1 plus f of 2, that modulus should be less than or equal to S of A, etc.
Yeah, and on defined to be. Find f of 1.
F of 1, we put all values and only selected values, possible values we draw. So it's not necessarily saturating, only the boundaries are some places it's saturating. In most cases, for example, we can put all vectors as 0. That is also a possibility because 0 is always less than or equal to. So even in space-time where there are infinite points, at each point we can define f to be 0, and it's just modulus 0 less than or equal to S of A. But the best case, like the boundary things contain the information, the boundary of the shapes contain all the entanglement substructure. Like I will just talk some applications, and like numerically, like we did not try calculating numerically, but like one of the problems with minimax and maximin, both originally, like I showed in some very like these formulas, minimax and maximin, they are not pure minimization or pure maximization. If you know one surface, you cannot say whether the optimal surface, like optimal S, will be less than or above that, because it's not. But in our case, the both U flows and V flows and U threads and V threads, these are pure minimization. V's are a pure maximization and U's are pure minimization. So if we know any arbitrary like value for the U flux, we know that the real thing will be less than that. Similarly, if we know V, we know the real thing will be more than that. So we can, for example, numerically put several, if you have some 100 examples of V threads, V flows defined, and 100 examples of U threads, that will probably get lost. that will probably give a good approximation to what is the actual value of S general, like the generalized entropy, the quantum external surface area. Yeah, like every time you guess one V flow, it gives an lower bound, and for U flow, it gives an upper bound. And another application is like deriving Einstein's equations. This is tried for the just the original RT formula. For original RT formula, many people derived this. I think Hartmann, Faulkner, and several other people derived it. And but these people, like their original derivation was already like generalization of this Ted-Jacobson's thing. But Ted-Jacobson only did for Killing horizons, and using the black hole has the property that area increases, and those properties he used and derived Einstein's equations. But that is only works for the black hole equation of motion. It does not say that it's true for arbitrary equation of motion. But in this case, they showed they generalized this, and like Ramsdorff, Faulkner, and Hartmann, and these people they showed that from RT formula there is using a property of entanglement called like the first law of entanglement entropy, and they mapped that to Einstein's equations in the bulk. And similarly, these people Egan and Cáceres, Elena Cáceres at UT Austin, and Pedraza, these people in 2020 generalized what they did for bit threads, and they did in this way. Normally, we think the metric is fixed, and then we consider all flows that are possible. We can do the reverse. If we already know our optimal solutions, then we can rebuild the metric by saying that we consider all possible, the metric should satisfy for every optimal solutions. So we know for every possible A. In the CFT side, we have any small region A, any random region A, and for all such regions A's, we know optimal solutions. If we know that, then we can rebuild the metric. They showed how to do that in the classical case. And maybe if we do in the quantum case, we didn't try, but like maybe we get the same Einstein's equations, but with T hat, maybe the operator. I don't know. I will just talk briefly about islands, and this is just an image taken from most of the images. Like I took from some review by Matt Hedrick, some lectures on entanglement entropy in 2019. These images, island images, are from this review by those people. And like islands, it's just like the information paradox is that Hawking's original calculation tells that they don't contain any information, they're purely thermal photons, and the entropy keeps increasing, and the black hole entropy keeps decreasing. But this is inconsistent because this number, when the evaporation is almost happening, the black hole has too few degrees of freedom. So if we assume it's an entanglement entropy, it's impossible. Entanglement entropy is always bounded from the property it's bounded by upper bounded by the smaller degrees of freedom quantity. So this cannot just keep going on, and we expect it should decrease after some time. And people like Don Page argued that we should get this kind of thing, and only if we get that, it's the information paradox is solved. And one approach to this is the island, it is still, I think, Andrea Scott, Subrat Raju, and some other people are they think this is wrong. But I think a lot of people do believe in this, and they just found some solutions to the gravity path integral that people did not see in the past. And if we include that correction, we have two things. One is with island and one is without island. The without island keeps increasing. This decreases, and we need to take at each point the minimum thing. So there is a phase transition when they are equal. Until then, it follows this green solution, then it follows the yellow solution. And finally, we started with a pure state, collapsed into black hole. We end with a lot of Hawking radiation, but it's not a thermal photons. It has a lot of entanglement, and it's a total pure state. And in bit threads, we can give this, but this thing violates locality badly. That is the one thing which is not seen normally in general relativity. We normally QFT and general relativity locality is respected, but in this case, what is happening is that somehow this interior black hole degrees of freedom are somehow the same as the far away photons. Before the island phase, it happens like this. These are the normal threads, and some covariant threads jumping and going like this. We are trying. Then this is the outside radiation entanglement wedge of that, and this is the interior. And here, what happens after some time, suddenly some phase transition happens, and this surface starts popping up, quantum external surface, and this thing like some threads are going in the back direction, so it's decreasing the S of A. So like this is the formula, like we need to include S bulk of both this thing and this blue region, and some of the entanglement entropy cancels out. There will be photons here and some other photons here, and they are entangled. But if we once include those two, their internal entanglement is not included in this S bulk, because we only look at the entanglement between this blue region and green region. So somehow, like non-locally, this far away photons, far away from black hole, like this interior degrees of freedom, and those are same. So somehow maybe some wormholes corrected or something. Like people, I think, don't know the correct interpretation, but they believe, a lot of people believe the calculations and think like. So in this case, like we need to calculate the flux on this side, but in this direction. But somehow they're going in the opposite direction and coming here. So they're decreasing the flux, so it cannot keep increasing. After some time it starts decreasing because of this and goes to 0. Yeah, like that's all I wanted to say. If are there any questions? We'll go to first few slides on any questions.
Maybe I have a couple of questions.
Yeah.
Could you try to just motivate the Bitthread program a little bit more, because at the end of the day, I see it as equivalent to, say, for example, the quantum extremal surface formula. But then I saw one place where you sort of motivated it, where maybe numerically it's more useful.
Yeah, numerically. Although conceptually, like when I showed this example, this thing, the phase transitions happen sudden jump. Like in this case, it suddenly jumps when these in the boundary CFT A and B are close. The minimal surface is connected, and then suddenly it jumps. So there is some discontinuity in this case. But in this case, whenever phase transitions happen in bit threads, they are continuous. So some continuous flows can be deformed like that. I don't know what is the use for that, but like on another, I think maybe like in some proofs like entropy cone or something, these might be useful. Entanglement entropy cone and those kind of things, it might be useful, but we haven't like tried that. But yeah, it's mostly just some conceptual explanation on like each thread is like measuring entanglement in terms of like it's like some line joining from one qubit that side to one qubit in A complement. So it gives some conceptual explanation. But yeah, mostly we just proved that it's the same as convection surface, and it gives some conceptual explanations in some cases.
But like other cases where using bit threads is like humanly more efficient than just using something like the maximum formula.
Yeah, I think numerically, like if we do in some computer, then it will be better. But if we are doing by hand in normally, then it's not better. Like in by hand, in all the JD gravity, they compute quantum extremal surface. It's always done like normally, like in the quantum extremal surface formula. In that case, the surface is just a point, so it's just the area is just the dilaton field at that point. And I think it's like if we're doing it by computer numerically, maybe it's useful. But if we are doing just also in generic surfaces, like people do compute only in time models where the areas are very simple to calculate. In higher dimensions, like the areas, like we need to extremize over, not even squarcially. If we are given some complicated metric, then it's generally very hard to how to find the minimal surfaces. I think minimal surface is also like I think many mathematicians also work on that, proving stuff about this. And I think there are many complications in some arbitrary metric and stuff. We are generally doing some simple metric, like even squarcial also we do in some 2D, like 3D or some like simple, in 3D BTZ black hole or in the 2D JT gravity or some very specific time models. We don't know how to do in some arbitrary metric in some 4D. In that case, it might be useful to have some pure minimization or pure maximization formula.
The original Bitthread was geometry, right? I mean, basically geometry is the notion of entanglement.
Yeah.
Now, with these sources, I'm not sure what the physical intuition. You certainly introduce source in the bulk, right?
Yeah.
So, is there a geometric description of that?
Like the physical thing, what is happening is that like it only like we are until now we are only assuming we know the macro state of that thing. So we S bulk we know, but we don't know the like there is a lot of degrees of freedom here in any, like in even the quantum covariant case, there is a lot of degrees of freedom in interior. But if we know, instead of just A, we also know, like only for A, we know all the homologous S bulks, like all the S bulk of gammas of all homologous surfaces. But if we know also like smaller regions than A, like instead of D of A, we have smaller regions inside D of A. And if we know all those things also, then we can probably put like they combine into a single bit thread, like instead of infinite things. If we know all the substructure of the entanglement, we are only assuming in the boundary we know just about A. Like we don't know about the smaller things about A. Like we know the macrostate of A, not about the fine details of the interior microstate of region smaller than A on the CFT. I think if we know all that, we can have a unique bit threads, probably like very small set or something. Like the degrees of freedom will be gone.
So is there a way to calculate S bulk using bit threads?
I think no, but like it is indirectly like if we know like it's just if we have two photons in the bulk, it's just a thread jumping from like here. If we have, for example, there will be thread like this and thread like this. Those just mean that there is a qubit here and qubit here, and they are entangled. Like these are not the only possibilities. There are other possibilities like this, and those things also contribute to the S bulk. And it is just if there are qubits and they have entanglement, like in the paper we also have some pictures, like, but I didn't include that. But like for tripartite, like these are continuous systems, so more complicated. For a tripartite entanglement for a state, like what are the possible bit threads? We can draw that. In that case, we have like we know all the microstate details. We just have ABC. We know S of A, S of AB, and all things. So in that case, it's like jumping, like there are like rotations. Like if we rotate the different things, we get 3 diagrams or something like that, bit threads, and they are the same thing physically. So indirectly, if we know all the microstates, it measures local entanglement between. It should be corresponding to like whenever there are threads here to here, that means there is some entanglement between here photons and like here matter and that matter. So otherwise there won't be those threads. So if we know all the like
suppose we use the quantum error correction code, right, to reconstruct the bulk. In that description, right, what are bit threads?
I think reconstruction in that case, earlier I was talking this paper by like Egon and this. I think that is the reconstruction approach. Like if we know all the, like we don't know the metric, we completely forget about the bulk metric, but we know all the possible flows and field lines. From that, we can reduce the metric, because the metric is the thing that limits like the non-bound and those things. From that only we can decide what are the possible flows. So based on looking at those flows, we can reconstruct the metric. So
I'm not asking about reconstructing it.
S bulk. You
Let's suppose that we have the reconstruction using the quantum error correction.
Yeah.
Right. Now, in that description, we can reproduce the HF formula.
Yeah.
Right. So then, in that description, is there a simple geometric interpretation of this bit threads? Right. I'm not asking for reconstruction using bit threads.
Okay.
Right. Imagine that you have used for a quantum error correction to describe the bulk of After that, can you understand what the bit threads are in that language?
I don't know. Like normally, it's just measuring number of entanglements between qubits. So every time there is a line, there is 1 qubit worth of entanglement between those points, like between A and A complement. I don't know, like that kind of geometric interpretation.
If there are no more questions, let's thank you.
Okay, thank you.
So if I know an optimal,
Hmm?
if I give you like an optimal solution of quantum covariant bit threads,
Yeah.
can I construct S bulk out of it?
Like S bulk of every homologous surface?
No,
Like
let's
that
say
one.
we fix a boundary here.
Yeah, it's just the number of endpoints inside the
Can
entanglement.
we calculate?
That is the S bulk of the,
Yeah,
yeah, like, yeah.
like I just gave you all the flux banks and
Yeah.
everything, and you can calculate.
Yeah, it says number of endpoints, so that is the S bulk. But we only know S bulk for that one thing. Like the final answer only gives that one thing. But for the input, we already had to give all the S bulks. Like
Why is that?
if we want to do convolutional surface, for every surface homologous to A, we need for every surface gamma homologous to A, we need S bulk because we are extremizing not just area. It's not giving S bulk. We are trying to measure S of A. Like S of A is the more mysterious quantity. S bulk, we are assuming we know S bulk. And
S bulk is the input, right?
yeah, S bulk is the input. Area is also input. But S of CFT is the output we are getting.
So till when are you around?
Tomorrow, I think 12:30 or something. I was there for 10 days, but I didn't know much people here, so I was just sitting in some corner. And I talked with mainly with two profs like Ashok Sen and Rajesh Gopakumar.
You were able to talk to them?
Yeah, I was talking with them. I need to.